nanohub.org.
Online simulation and more for nanotechnology.
Well, welcome back. This is the last module for week 1, and seems like a good time to just quickly summarize what we achieved. And I tried to put that up here. See, back in module 1, the point I tried to make is that this week we were going to talk about this new Ohm's law. And by Ohm's law, I said it means this idea that resistance is proportional to the length. So it's resistivity times length over W. And what I said is, what you'd see as you go to ballistic transport, that means when you go to really small devices, just that expression, that Ohm's law would have said that as length goes to 0, resistance should go to 0. And the point is, it doesn't really go to 0, it goes to some other constant value. And that is the part that I had indicated could be written as by modifying length with length plus something like mean free path. That's what I stated back in module 1. And then in course of these modules, we finally obtained expressions which I have summarized here, that the conductance can be written as kind of an average over this conductance at different energies. And then what we said is, let's look at conductance at a particular energy and the conductivity. And the conductivity can be given by this product of density of states and diffusion coefficient. Then there's this ballistic conductance, which depends on density of states and average velocity. And the conductivity can be written in the form of, in terms of the ballistic conductance, in this form. And you could think of it as if there is an additional resistance sort of in series with the regular resistance. That is, you see, Ohm's law tells you that the resistance of this part should be proportional to this length. And what we are saying is when length goes to 0, gets to be really small, the resistance doesn't go to 0. There is a constant resistance. And that constant resistance you could view as something in series with the resistance of the channel itself. It is as if the resistance of the channel itself is rho L over W. This part is just rho L over W. That's in here. And then, as if you got some additional resistance, which is this ballistic resistance, the inverse of the ballistic conductance. That is what you could view as additional resistors here. And people interpret that as an interface resistance, something that arises from the interface between the channel and these large contacts. Now, one important conceptual point that I want to stress here is that when you have, one of the reasons why people always assumed, or there was always this argument that when you make something really small, the resistance should go to 0. The thinking was that when you make something small, an electron can go from left to right without exchanging any energy with its surroundings. So when you look in this picture, electron just goes from here to there. And if it came in with a certain energy, it exits with exactly the same energy, doesn't give up or absorb any energy from its surroundings. Now, if so, then question is, how is the heat generated? What I mean by that is that if there's a resistance, one of the things that people knew is that anytime current flows through a resistance, there is what's called the Joule heating, I squared R, or sometimes you write it as V times I, because I times R is voltage, so V times I. And if there is a non-zero resistance, the point is there is a heat generated somewhere. And heat generation involves the electron giving up some of its energy to the surroundings. Because how does a solid get heated? Well, because you'd say the electron is zipping through it, And as it goes through, it loses some energy. Loses some energy meaning there is this solid with all the atoms in their position and they take up some energy from the electron and start jiggling, because heat basically is the jiggling of those atoms. As you know, if a solid, you can cool it to very low temperatures, then all the atoms would be frozen in place. But as you raise the temperature, they start jiggling around because of the thermal energy. And in fact, when they jiggle too much, that's when the solid melts. But if you are way below the melting point, they still jiggle, but not enough to melt. So it's like if the distance between two atoms is, say, 0.3 nanometers, 3 angstroms, 0.3 nanometers, then the amount to jiggle would be like maybe 1/100th of that at room temperature. But the point is they jiggle around. And as the electron moves through, they can give up some energy to those atoms, so they jiggle a little more. And that's what would be like heat. But in small devices then, it's like you can almost assume that the electron doesn't exchange any energy. And then the question is, but we are calculating a resistance, sure enough, and there's a current, so there's a heat. So where is the heat? How is the heat getting generated then? And that's where the present view is, the understanding is, that you see, the electron, once it comes out here, inside the contact, it has a lot more energy than it should have. Why? Because this contact, when it is in equilibrium, all electrons occupy energy levels up to μ2, up to this electrochemical potential. And here is one electron by itself with a lot more energy than all its neighbors. Everyone else is down here. So it's got a lot of excess energy, and what the contact does is it quickly restores it to equilibrium. And that is where, of course, the electron loses all its energy. And same here, the electron that left this place kind of left an empty spot behind, and all these electrons quickly lose energy and get in there. So the point is that this I squared R, this heating, that every time an electron goes from here to there, it gives up an amount of energy equal to the V applied. Namely, if 1 millivolt is applied across this, then an electron going from here to there loses an amount of energy 1 millielectron volt. But where is that energy? Well, it's partly on this contact and partly on this contact, but hardly anything in the middle. And this is a picture that seems to be reasonably accurate for small conductors. It's not true at all for big conductors. For big conductors, electron is losing energy all the way. So that 1 millielectron volt that I said is distributed along the way. It loses a little bit here, a little bit there, a little bit there. Everything gets hot. The entire thing gets hot. Whereas when you take small carbon nanotubes and the electron and people run currents through it, the belief is that what gets hot is the contacts, not the nanotube itself, not this channel itself. And that is, there's experimental evidence for this, in the sense that if all that heat were actually dissipated in the nanotube, it would have melted, because that small thing, there's no way it can get rid of that much heat. But the understanding is the reason it doesn't melt is that the heat is not dissipated in this small little thing here, but rather it is dissipated in this very big contacts. And the big contacts, of course, can get rid of the heat easily, and so it doesn't melt. So today's nano devices, this picture is believed to be a reasonably accurate way of thinking about things. And that is actually what helped us a lot in terms of whatever we did this week. Because we said that electrons go from one end to the other at the same energy, whatever energy it starts out at. So what that means is all these different energies where the electron could be traveling, they're all independent paths. Namely, you have some conduction through that one, some conduction through this one, some through this one, but once you are in a particular energy channel, you are not allowed to change lanes. You are not allowed to go up and down in energy. You just stick to that. So what that means is when I'm calculating current, I can try to figure out what happens in this channel and what happens in this channel and what happens in this channel all separately, and then just add them up as I've done in this integral. That was this integral. What it shows you is you can think of the conduction through one energy channel and then just average it over energy, sort of, because you've got all these things in parallel carrying current. Now, this is something one wouldn't be able to do if you had a distributed process of energy loss, because then what would happen is you'd have a situation where your electron starts out in some energy channel, goes to some other energy, then maybe picks up some energy, goes somewhere else, loses some energy here, etc. So it's like everything would all be mixed up, and you'd have to keep track of flows of all energies together. You couldn't just do it one energy channel at a time. So this picture that I used here, that's what you call the where electron does not lose energy, getting from left to right. That's what one calls, what we have called in the notes that you can look up, the elastic resistor. Because elastic is that in physics usually a collision is said to be elastic if no heat is dissipated. So here we are saying it is the basic resistor. This, when the current flow, how much current flows is of course determined by this narrow region, not by the contacts. The contacts are out there, those are big puddles, big regions. So it's like you have a few lanes here which are fed by hundreds of lanes. So of course the entire traffic is controlled by those few lanes. And then here, that's what determines the resistance. And yet, that's not where the heat is dissipated. The resistance is determined by the channel. But the associated heat, the I squared R, that's somewhere else. That's in the contacts. And so the resistor itself is kind of elastic. And this is the thing that 20, 30 years ago, if I had said we were talking about elastic resistors, people would say, well, that's nonsense. You can't talk about elastic resistors. A resistor dissipates heat. So it doesn't make any sense to talk about elastic resistor. That's how they would say. And so, usually when people think about resistance, actually before 1990 or so, before all these experiments on small conductors came along, people never worried too much about contacts and things like that, because resistance was essentially about the loss of energy inside this channel itself. So that was a very important part of calculating resistance. Whereas, what we have now done is we are talking about these small conductors where hardly any energy is lost here, actually. And the contacts are, of course, very important in this description. So it's a whole different view of how we think about this. So traditionally, when we think of transport theory, people normally don't think too much about the contacts. They worry more about how electrons are losing energy inside the channel. And they try to calculate these dissipative processes inside the channel. Whereas for small devices, a much better approximation is to ignore it completely and then include it as needed as a higher order correction. So this view, this what I called here the elastic resistor, this way of thinking, I guess it dates back to Rolf Landauer, who was thinking of this as a model with which to understand the flow of anything really, of transport in general. And he was proposing it more as a conceptual tool, because what makes transport theory so complicated is the fact that these two types of things are mixed up. That usually this process, the process by which electrons travel at the same energy, and the process by which electrons lose energy, those two things usually are mixed up, and that's what often makes transport theory relatively complicated. And Rolf Landauer was thinking of a model where you could separate out the two. And that was back around 1960 or so. But for many years, actually, no one paid much attention to it because people said, well, this is just an academic thing. It's not really like the real resistors. So it doesn't get you very far. But then in the 1980s and 90s, when people started looking at small conductors, that's when suddenly this Landauer's model became very relevant because real devices were actually behaving just this way, like an elastic resistor, where energy was actually dissipated much in the contacts. But the point I want to stress is that this conceptual viewpoint is really very useful because it separates out these two types of things here. See? Now, what you might say is, okay, but how can you find the conductivity? You see, that expression, as I mentioned, that we obtained this week, that expression in the usual way takes a lot more work. You'd have to discuss all kinds of advanced formalisms. As I said, either the Kubo formalism or the Boltzmann method, which is why in textbooks it's like chapter 13, because it comes a lot later. Whereas here we could get to it much faster. But what you might say is, yeah, but then that usually applies to long conductors. So how can you analyze a short conductor like this and get that result? Now that's what I've tried to indicate in the slide on the right, that when you have a long conductor, you could mentally think of it as if you got lots of short conductors. So as if an electron goes through this part elastically through one conductor, loses some energy, and then again goes elastically for a while, and then loses some energy, etc. And so one could think of a long conductor as lots of little elastic conductors like the ones we analyzed. Now, but this is tricky. And I mean, you could say, well, this is something one could use at least for low bias. And essentially that's what we did. But it's a little tricky because of this extra interface resistance that I mentioned. That, you see, when you analyze a small conductor like this, not only do you get a resistance here, but also this interface resistance associated with the two interfaces. And similarly, here also you get all these interface resistances. Every time you introduce one of these conceptual contacts, there's an associated interface resistance. And so if you just find the resistance of this and add that, you'd have added all these interface resistances, one after the other. And that would be wrong, because the real device, of course, does not have those interfaces. Those interfaces are just conceptual. So those are not really supposed to be there anyway. So what that means is, I'd said that the Ohm's law is modified to look something like rho over W times L plus lambda. Okay, and as I said, this is the resistance of the actual channel. That's the interface part of it. Good. So what if I put two of them in series? If I take a big one, which is of length 2L, and I think of them as composed of two small things. Well, it would be completely wrong if you just multiply by 2 here. That would be wrong. Because if you do that, you're not only multiplying the channel length by 2, but you're also getting the interface resistance, twice the interface resistance. And of course, this intermediate interface is not really there. So the correct answer would be more like rho over W times 2L plus lambda. So in other words, when you make something longer, this part becomes 2L if you made it double, but the interface part stays the same. And again, there are many experiments back in the 90s which show this quite clearly, that if you put, so for example, if you take two ballistic resistors are where this L part of it is almost negligible. Then the point is, if you take two ballistic resistors and put them in series, the overall thing is still a ballistic resistor. It's twice as long, but the resistance shouldn't be doubled. It should essentially stay the same. Anyway, so with this is the important conceptual point that 20, 30 years ago wasn't at all clear. Which is why if you tried to think of big conductors as lots of little things in series, you'd get very confused, because you wouldn't know how to use that viewpoint. But now that people understand this interface resistance clearly, it is possible now to use this viewpoint of small conductors, these elastic resistors, and think of a big conductor as lots of these in series. And that viewpoint gets you a lot of these standard results, like this result for the conductivity that I mentioned. This is, as I said, a standard result. But we can get it much faster, as we did this week, by using this viewpoint that if we had a big conductor, we'd just think of them as lots of little ones in series. In a bigger sense, this is why I feel that this small conductors gives you a whole different perspective on transport in general. And that's because, you see, in transport theory, what really complicates things, as I mentioned before, is that these two types of processes are mixed up. You see, in physics, there were these two very distinct branches that evolved separately. First was mechanics, which is Newton's laws, which came from observing planetary motion, frictionless motion of how the planets move. That's mechanics. Several hundred years later came all the heat engines, and people understood that heat was a form of energy and how heat can be converted to other forms of energy. That's the science of thermodynamics. And so this part, this elastic part, that's mechanics. That's when an electron goes from left to right, exchanges energy with nothing else. That's like planetary motion. That's mechanics. This part of it, where it gives up heat to the surroundings, that's where thermodynamics, Fermi functions, all that comes in. And in the usual transport theory, what happens is those two things are mixed up. And that is why you cannot just use Newton's law to analyze devices. What is used to analyze transport, not only of electrons in devices, but of all kinds of particles, of neutrons in reactors, and so on, is the Boltzmann transport equation. That's this BTE, what I've written there as BTE. And what it does is, it takes Newton's laws, but adds a description of this part, this kind of processes into it. And that is a non-trivial step. You see, that is what kind of took all of 19th century. And Boltzmann equation was something that developed at the end of the 19th century, and in its time was very controversial. I mean, he kind of died somewhat broken-hearted because a lot of the people in his day didn't quite accept what he had done. It was subtle enough that, it took time to sink in. And even now people argue about that somewhat. And the same with quantum transport. It's like, instead of Newton, we have Schrödinger equation. That's the quantum mechanics. But that too has to be kind of supplemented with processes of this type. And that then leads to this non-equilibrium green function method that we talk in the part 2 of this course. That is where we discuss those issues. But the point I'm trying to make is, in general, it is this mixing that is conceptually hard and that has taken a lot of time over the years, a lot of effort and genius to actually sort out over the years. And by contrast, when you look at small devices, the two processes are separate. And so you can use mechanics to analyze how electrons get through. And then when the complicated processes happen, you kind of you can handle it very easily simply by saying that, well, when you get there, what happens is the contact always maintains everything in an equilibrium distribution, this Fermi distribution. So this contact is always maintained according to F2, and that contact is always maintained according to F1. And so current depends on F1 minus F2. So with that one statement, we have kind of bypassed all the complicated processes that lead to this restoration of equilibrium inside the contacts. And that is essentially what allows us to get profound results like this relatively easily. And of course, in the process, we also are able to treat things like ballistic transport, which is what, and these are things we'll talk further about then in next week.